We're now going to take a look at some integrals involving the natural exponential function e to the x. So recall that the derivative of the natural exponential function e to the x equals e to the x. That's the only function whose derivative is itself. Now, since we have this property holding, we then have this. So the indefinite integral of e to the x is e to the x plus c. And that's because if we were to differentiate this side right here, we would get back e to the x power, right? Because d dx right? When we differentiate e to the x plus c, just break this up as the derivative of e to the x plus the derivative of a constant, which is 0, and of course we get back e to the x. So now we can use this to evaluate some antiderivatives. So let's take a look at these examples down here. So let's find the antiderivative, the indefinite integral, of x times e to the x squared power. So what we're going to do here is we're going to try a substitution. We want to turn this into something that looks like this up here. So what we're going to do here is we're going to let u equal the x squared term that's in the exponent right here. Then you see du is going to become 2x dx. And then just dividing the 2 to the other side, we get that du over 2 equals x dx. And now we can do the substitutions in here. So the x squared here will become a u, and the x dx part right here will become du over 2. And so performing our substitutions in here, this integral will become and now you see we've turned the integral into something that looks like this up here. And so the antiderivative of e to the u is just going to be e to the u. The u is playing the role of the x up here. And we end up with, so there's our antiderivative, or our indefinite integral. And making the substitution, what u was x squared, and so we get and there's our answer. And you can check that the derivative of this does give you back x e to the x squared. For example, if we were to differentiate this, so if we differentiate this, we'll get 1/2. We have to use the chain rule when we differentiate this, so we let u equal x squared, so it's going to be e to the u times du dx, which is 2x, and then the derivative of the c is 0, and we end up with the 2's canceling here, which is what we wanted over here, x e to the x squared. Now let's take a look at this problem. So here we want to evaluate the definite integral from 0 to 1 of e to the x divided by 1 plus e to the x. So once again, we want to try a substitution here. So we're going to let u be the denominator here. In which case then du is e to the x dx. You see the derivative of 1 is 0, and the derivative of e to the x is e to the x. So this piece right here is the derivative of this, and we end up with this. And now, using these values to substitute into our integral, let's notice that the e to the x dx part, that becomes du, and the denominator, 1 plus e to the x, is u. So then this definite integral will become And now we have to change our limits of integration. So what's in the bottom limit of integration is going to be u of 0, and the upper is going to be u of 1. Now if I put 0 in for the x right here, we're going to get 1 plus 1, which is 2. And if I put 1 in here for the x, we're going to get 1 plus e. Now the antiderivative of 1 over u, well, that's the natural logarithm. And we evaluate that from 2 to, and this becomes, and if you like, you can simplify that as, and then you can evaluate that on your calculator, and that value is approximately 0.6566. And that concludes our discussion about integrals involving the natural exponential function.